Right, okay, so for the last talk of this morning, very pleased to have Jacopo De Nardis from University of Cergy, who's going to tell us a bit more about GHD and also take us through, there's an acronym here, GBBGKY, or weakly non-integrable systems. So hopefully that will be demystified.
Yeah, so GBBGKY is stands for Bogoliubov. What's the second? It's a known hierarchy for kinetic and kinetic theory, which here we will generalize like almost 10 years ago we have generalized hydrodynamics, like GHD. Okay, so this work has been done mostly with and by my PhD student, Leonardo De and also with collaborators in Warsaw, Miłosz Manfil and Maciej Lewek. And okay, and since of course you heard a lot about GHD, let me just reintroduce it again since repetita iubat. And the way I like to introduce GHD, indeed, it's with hard rods, because indeed it's the simplest system that you can do GHD with. And okay, I guess there's room, there's no need to introduce hard rods, so now I don't know what to do, but okay, let me repeat it again. So hard rods, it's a model for spheres that just are impenetrable. So when they scatter, they just change their velocity. So the way you model the scatterings, that instead of following the particle that keep changing the velocity, you just follow the particle that keep the same velocity, right? And this is what you call tracer, and this is exactly what you call quasiparticle in GHD. That's why the quasiparticle in GHD keep the same velocity. So if you follow indeed the trajectory, you see that this quasiparticle every time scatter jump of a length a, where a is the radius of the hard rods, and it follows some kind of stochastic trajectory. If you actually coarse grain this stochastic trajectory, you see that late time it goes through some kind of a velocity. So its motion is like as a fixed velocity, which is basically the rest velocity, because it depends on the amount of rate of scattering that you have in your system. But also, it's also spread. This trajectory is spread in time, actually spread with square root of time. So this tells you that indeed there is diffusion in the system. So the hydrodynamic for hard rods indeed has been developed by these great peoples. And the way to think about it is simply that you coarse grain your system into fluid cell. And in each fluid cell, you put enough hard rods that you can talk about the density of velocity here, theta, the velocity of momenta at each position, space, and time. And what you see is that indeed there is a convective flow given by the effective velocity times the density, where this effective velocity, you can write it down, and indeed, basically, it's the bare velocity, which is the theta, plus the correction due to all the scattering from the left or all the scattering from the right, and indeed it's proportional to A. But there is also indeed diffusion spreading, and diffusion spreading is regulated by a diffusion matrix, which takes the form of a Markov-like matrix, which has to do with indeed basically this kind of Markov process that a quasiparticle undergoes every time it's scattered with another one. Now, this has been derived in the 80s. And I think like the greatest achievement of generalized hydrodynamics has been really to take the theories that have been basically developed in the 70s and the 80s, and for the hard rods, and meanwhile also by the soliton gases, and basically just generalize it to generic integrable systems. Because the idea is very simple, that in hard rods, you have a scattering that indeed depends on the length of the rod, A, and you follow indeed the quasiparticle that conserve the same velocity. In generic, classical, or quantum integral system, you always have a phase shift, which typically you write with t, which is a function of theta and theta prime. And basically, the phase delay that you have is t divided k prime. So this is actually the phase shift. Sorry, t is the scattering speed. And now this becomes the effective dimension of these rods. So basically now you have rods that whose length depends on the momentum of scattering, but then they behave exactly like hard rods. And basically then now you can do any integrable model you want. I'm just writing some of them here, both quantum or classical. So there is a universal equation for the effective velocity, where basically here you just take the result for hard rods and you substitute A with the scattering shift. There is a universal dressing equation, which Thibault has written before. And here it's written as an operator acting on a function. So for any bare function you want, for example, energy, theta squared, you want to dress it. When you have a finite background, then you apply this linear operator where T is the scattering shift and N is the filling of the particle inside. And there is a universal hydrodynamic equation, which also includes diffusive terms. So indeed, I mean, this talk will be mostly about these diffusive terms, so something new compared to what we've seen before. These diffusive terms, indeed, you can, in order to derive them, you need to do some work. This is originally what we did by computing the Kubo formula, but then we found out other ways to there are simple ways to understand them. Sorry, I was checking if I put the slide or not, but I think it will come later. Anyway, so what is the topic of this talk? The topic of this talk is actually now, okay, great. We have a GHD equation. This actually has been proven useful in a lot of settings, like quantum cold atom system, classical solid-on gases, and so on. But since integrable system, but this is really for a purely integrable situation, right? Where the Hamiltonian or the PDE is exactly integrable. But in a lot of physical situations, there are breaking of integrability. As Thibault already mentioned, you can basically imagine that the particles are inside some external potential, for example, the trapping potential. This is one way to break integrability, where you basically add to the integrable Hamiltonian, you add an external field coupled to some conserved density. So by the way, this Q0 is just the density, right? If I integrate it, I get a total conserved charge. So this could be the density, this could be the energy density, anything you like. And another way to break integrability is that, okay, imagine that this is your hard rod's potential, right? But now imagine that there is an extra longer range potential that acts between the particles. This is also a physical situation. And so how we deal with these situations? So let's first look at this one. This is the one you already seen in the Benjamin and Thibault talk. Basically, you have to understand GHD as a two-dimensional fluid. So you have, so I'd like to introduce this nabla, which tell you that there is a flow in X space, right? And the flow in theta space. So the flow in X space is given by the effective velocity, and the flow in theta space is given by the effective acceleration. It really works the same, like when effective velocity is dressed by the effective particle scatter, and therefore they take an effective direction, the effectivization of the acceleration is really just the same, works the same. But there is also viscous terms in each direction, in xx, in x theta, in theta x, and theta theta. And they really this become like as I mentioned already, like a continuity equation for a fluid in 2 dimensions. Okay, and how do we understand this? But again, if you take hard rods, it's really easy to derive this equation. You can think of a generic external potential in hard rods. For example, you can imagine that there is a mass term that depends on x. This corresponds to coupling the external field to the mass and therefore to the energy, to the kinetic energy. Or there can also be an external potential. This indeed corresponds to coupling the external field to the density. And basically, okay, if you can write the single particle equation of motion, and you can simulate easily this system. And basically, what you see is that indeed, for each particle, x dot is given by its effective velocity, which depends on rho, on the local density in around the particle, but also theta dots depends on the effective on the rho, on the density of particle around. So how to understand this diffusive term? This diffusive term really comes from the fact that the density fluctuates in space, right? It fluctuates in space because there is an initial random configuration of rods which are propagate, and then you have fluctuation in space and time. So the position of the particle around its mean value, the velocity, oscillates, fluctuates with some square root of t. So basically, the fluctuation of the position divided square root of t is exactly what gives me this diffusion in space. Again, I can do this for the correlated fluctuation in space and theta. This gives me some diffusion in x and theta. Okay, and again, also there is, because acceleration also depends on rho. Can you imagine that differently in space and time there are fluctuations in the acceleration that also define some spreading in the acceleration. So that's exactly a kinetic way to obtain these diffusion terms. Now, of course, here I'm just wiggling and not giving exactly the formula, but you can derive exact formulas in many ways, either indeed really computing exactly these spreadings, this fluctuation, if you want, that are like correction to the mean, which is an effective loss acceleration, or using more complicated techniques like matrix elements for the quantum integrable system and summing them, or even using hydrodynamic projection. So now we have actually 3 independent ways to derive this diffusion term. Okay, so why do we care about these diffusion terms? It's because we should expect that when I'm breaking integrability, so when I'm adding external forces, the system is not integrable anymore. And if a system is not integrable, it should thermalize. If I'm doing some non-equilibrium protocol, the system should evolve, but at some point its steady state should not be anymore a GG, should not be anymore a state where I can have any distribution of quasi-particle. It should be a thermal state. Entropy should increase. And this is exactly what you see. And but in order to see it, you exactly need to have diffusion. So I'm not gonna go into a lot of details about that, but basically imagine that you're starting from a state like this, which is like some homogeneous state in space, and there are like 2 peaks on momentum for the quasi-particle. So there is half quasi-particle going left, half quasi-particle going right, and you put them into here in a cosine potential. So now there's going to be a lot of chaotic motion in the phase space. Actually, if you really go at short times, you're going to see like crazy figures like this. What happened is that there is a kind of, in this phase is what really is regulated by this Euler-like dynamics, okay? And really has to do with the fact that this fluid is like turning due to this flow. But at late time, the viscosities this time actually redistribute all these singularities. So all these weird wiggles basically get splashed out, and you get something like smooth and homogeneous. That's when actually you start thermalizing, and you see that entropy increase. And basically, if you look at some, for example, local operator, here in this case is the kurtosis of the momentum distribution. Basically, you see that there is some like path motion, okay, which is regulated by the Euler time scale. So indeed, this is time divided time Euler. At order 1, you see that the black one is the prediction just of this equation. You see that it really well predicts the first oscillations, but then at late time, indeed, you see this slow crossover to the thermal expectation value. This one regulated exactly by the diffusion term. So it's really the same picture that you expect if you put ink in a fluid and you mix it, you're gonna see all this fine structure, but then at late time, every diffusion viscosity redistribute. How much time do I have?
12 minutes.
Okay, so this was a major, this was really great to understand this because at least in the community where I come from, which is more the quantum cold atom community, there was really, people really wanted to understand how external forces break integrability and how to see this, how to see thermalization. And indeed, really, thermalization can be seen really from GHD tools. That's the amazing thing. And it really has to do with the viscosity that are present in this. But now let's look at a different case. Now I look at a case where basically I don't have an external fields anymore. So these are two conceptually different cases. I don't have an external fields anymore, but still I perturb my integrable system with an extra interaction. So indeed, exactly like for our rods, which will be like this infinite potential at distance A, there can be a longer range interaction at this typical distance. Okay, so this will be the total potential between the particles. So how do we deal with this situation? So if I have a free gas, if I imagine that A is 0 and I consider perturbation of a free gas, indeed, the way to do it is going with this BBGKY hierarchy. Okay. So what BBGKY hierarchy is? Okay, I guess many of you have heard of this, but basically it's really like the way to derive even hydrodynamics, really from a kinetic picture standpoint. You start with the density of quasiparticles, and then basically you see that interaction creates correlations, create 2-point correlations, but it can create also 3-point correlations, basically can create correlation at any point, right? Any multi-point correlation are basically created by interaction. So I made this figure, which I think is quite instructive. So basically, imagine that you have like two independent particles, they interact with this long-range potential, they correlate, so they create 2-point correlations. Now, this 2-point correlation can do two things, either to spread, because there is always like a spreading of the correlations, or also of the particles, right? So either they spread, so with some kinetic term that had to do with the velocities of these particles, or they scatter with another particle and they create 3-point correlations, and so on, and so on, and so on. So that's the hierarchy, which typically people truncate, because of course you cannot go to an infinite order. They truncate. And if they want to see, for example, thermalization, the relevant thermalization scale, they truncate to the 3-point correlations. You cannot truncate, if you truncate to the 2-point correlation, actually, you're not going to see any thermalization in one dimension. This is known as kinetic blocking. But if you include 3-point correlation, basically, which is like basically including 3 scattering terms, then you can see thermalization. And basically, if you solve by, there are some techniques to basically approximate the 3-point correlation, plug it inside the solution for the 2-point function, and then solve it and plug it again to the equation for the quasiparticle, and this give you Boltzmann equation. Okay, and you see that there is some thermalization time scale, which is order V0. So V0 is the external field, the external this extra interaction to power 4. Power 4 because you have to go to 3-point correlation. So you have like 2 steps. This is square, this is 4. Now, what we actually wanted to do is to generalize BBGKY to interact in integrable systems that are perturbed. Okay? And how do you do that? Well, basically, you have to take into account 2 major differences that perturbed free gases have with interacting systems. So the first one is that now, as I told you, like particles can scatter, create correlations, okay? And now these correlations can do 2 things, again, either scatter with other particles and create high-order correlation, or propagate. But now, the propagation of the correlation is given by GHD, namely some kind of generalized GHD that now is not for the density, but it's for the correlations. And you can write the evolution of correlation with GHD, which indeed contain effective velocity. Now, this I wrote it, this is the flux Jacobian that Benjamin introduced you, but also diffusive terms. So basically, that's what represents here the wiggle, the fact that this correlation spread with diffusion, which you can see it as an effect that while they are spreading, they're actually still scattering with other particles in the system. They don't correlate, but these other particles basically give them some stochastic motion. The other difference is that now, even at time zero, before to actually see that there is an extra potential, particle can already be correlated because of the integrability structure. So now you can create a higher difference, higher point function, where basically you can get correlation between one single particle and two particles that are correlated by the integrable interaction. So this complicated a bit the structure. So we had to invent like a different way to do partitions between these correlations. Just write in the question, the two equations. So this would be for the two level of the hierarchy. I'm not going to explain all the symbolism. It's a bit complicated, but basically you can write it down. You can write it down, and again, our diffusion is actually what gives thermalization. So now particle can just correlate because of the external of the extra force, of the extra potential. Then they spread, and this spread basically take into account these three body scatterings that are necessary for thermalization. And now thermalization time is actually very different compared to a free gas. It goes with B0 squared, which is times A, which A is the radius of, if you want, is the strength of your interval interaction. And now, again, we can do a simulation of hard rods. We take hard rods and we add an extra long-range potential of this type, for example. And what you see is that even at reasonably high interaction with 0, 4, and 8, you can, this BBGKY just at the second layer completely reproduce the dynamics and also the thermalization dynamics, which is this exponentially decay of, for example, again, of the kurtosis of the density quasiparticle. By the way, the kurtosis of the density quasiparticle, if the system thermalized, has to go to 0 because thermal system by Marx and Boltzmann is described by Gauss. So on top of that, you can also see really the development of correlations. Initially, you have 0 correlations because I have subtracted the integrable part, so it's 0 correlation. But because of the action of this long-range potential, you have the rods start to correlate, and basically you miss some finite time effect because, of course, this you can imagine that would be higher order in the hierarchy, but at late time you really get how the correlation should be, which basically are more or less related to the strength of the final potential. By the way, hard rods with extra potential, it's something that again has been considered already in the 70s, 80s, mostly at equilibrium. So people were actually asking indeed, what's the thermal state of hard rods with the standard potential? They have wrote several results. Okay, and we have compared that at least the stationary state is more or less compatible with what we were saying. They were doing mostly perturbation expansion a bit. So again, now you can, if you do those approximation and you solve the equation for the 2-point correlation, you can time integrate it, put it in the equation for the density of particle, and you find Boltzmann equation. Boltzmann equation is always an equation of the type dt rho equal some functional of theta and rho, okay? Which is typically nonlinear, and it has all different properties. First of all, it has to conserve the conserved quantity that has to be conserved, like for example, number of particles, total energy, total momentum. Typically, these three are conserved. Indeed, the stationary state is thermal. It also has to increase entropy, which you can see. And okay, again, the expression is a bit complicated, but you can see that basically this D and A are just related to the flux Jacobian and diffusion matrix. And basically, the first non-trivial part of this scattering current, it has to do with K D times A. So basically, it's linearly proportional to the diffusion. So that's what indeed confirmed this thermalization time of order V0 square times A square, because diffusion is indeed order A square. It's proportional to the scattering, to the length of the rods over 2. It has to do with 2-point scattering between the rods. And okay, so basically, in a sense, what we have learned is that even if for any system which are close to integrability, around there is a whole, so this is basically expand our region of applicability of GHD, or if you want kinetic theory based on GHD, to really a lot of system. Now we are not restricted only to work with exactly integrable models, but we have like regions which are basically order perturbation square around each integrable system. What really we can compute the dynamics completely at every time step, which is quite amazing. And again, okay, maybe I'm a bit biased because I derived these diffusion terms, but I think that really this is all we had to all we needed to understand integrability breaking was really hidden in the viscosity, in the diffusion term of the integrable theory. This gives us all the basically Boltzmann term and time scale for thermalisation under integrability breaking. And then, okay, this is a dream that I have, and I would like if some of you have any idea. So what we know is that if we take a free gas and we perturb it, you can observe like some fancy phenomena like wave turbulence. This typically in free gas of waves, but this is no. Now, what happens if instead of taking the free gas, we take an interacting interval gas and we add perturbation? Then we have a generalized wave turbulence. So, which would be like some kind of a interesting stationary state of the Boltzmann equation for integrable system, perturbed intervals. And with that, no, thank you.
Yes, so you have a specific integrative breaking potentials QQ potential Q0 Q0 D of X minus 5. Can you do some similar method for something more general? But what kind of information you?
Yes, here you can put any conserved density.
Yeah, so any bilinear conserved density.
Any bilinear conserved density.
I guess you can go to hydrodynamic, trilinear or something like that.
Yeah, I mean, yes, it's just a matter of repeat, like visualize the BBGKY. Yes, but basically the starting point of BBGKY is always like the Liouville equation. So you write the operatorial the equation for the density charge. Once you have that, then you know what output.
Maybe I understood the problem of thermalization. Like I know that they quickly interact with the integrable system with the Boltzmann equation and dimensionalize the screen plus say lambda integrated with the term at the mediation time usually lambda square. Then here we're showing lambda
No, it is V0 square. But it's V0 square only for interact if you prefer interactive integrable.
I'm saying that the Boltzmann equation is 3 plus as more interactive, that's Weber's integrability, and this gives you usually a term that is quadratic.
No, it's quite.
I plenty of literature on that.
No, it's quite.
Of course, one is your
The body scattering cannot redistribute momentum.
If there's if the induction term is not it's not a small operator, but it's a free molecule lead, for example, that will be a
No, this is for two body terms.
there's a hypothesis in the form of the.
So, I mean, the hypothesis is this.
Okay, so this
just a simple question, just double check. But understand correctly what we did. So it's not solving really all the right? Take this correlator and see if it's possible flow.
Yeah, no one can solve it.
Yeah, of course, I'm just make sure.
Yes. In this plot here, we are numerically solving the hierarchy. We are truncating to level 2. Yeah.
So, can you assure in your structure that the diffusion matrix is actually we don't run into anti-diffusion?
It's positive. Yes.
It's a consequence of the construction, and you can show it.
It really comes from the way you define it, but you can go back to the I just wrote it for the hard rods, and this form is universal. It always takes the same form. It's always a Markov-like operator, where the V are the scattering amplitude. So it's like the probability of scattering with another particle. So these are always positive. These V are positive, and then this matrix is always positive decimals. It's really the way our.
We have a question online. Stefan, you can unmute yourself.
Yeah, thank you. Wonderful talk. I have a couple of questions. What can you tell me about the structure of this diffusion matrix? Is it symmetric?
Again, it's really, it always takes this kind of form. If the diffusion is not symmetric, it's diffusion times susceptibility, which is symmetric. This is not symmetric, but basically it always has this form. It has to do with the fact that you have like diagonal elements, which has to do with basically has to do with the spreading of the. So this spreading of the trajectory of the quasiparticle is really just given by the diagonal term. The off-diagonal terms are there just to enforce that there is, for example, some conservation law in diffusion. For example, I want that density, if I integrate over theta here, I want that this is 0. Why? Because if I integrate over theta here, for example, I get the equation for total density. And the equation for total density has no diffusion. Why? Because the current of total density is momentum, and momentum is also a constant quantity, which therefore cannot have diffusion. So if you want the way you derive it, there could be like a way to I don't know, but there could be a way to derive this matrix, basically just imposing some basic kinetic term with some kinetic scattering rule, and imposing also some symmetry, like for example that total momentum is conserved.
And if I could, the second question relates to the choice of potential, the interaction potential. Have you considered using perhaps, say, a Leonard-Jones potential?
Yeah. This we actually exactly. So what we have in mind is exactly Leonard-Jones. We want to see basically hard rods. If you want hard rods or linear, whatever it matters, like the infinite potential at 0 as a way to describe the divergence of the potential at short range, and the smooth part as the perturbation. And of course, here I did it for a passive, but I can also do there's no restriction on the sign of this guy. It can be negative. Yes. So Leonard-Jones is exactly what we have in mind.
So the reason for asking that was because of the critical point where you would have a phase transition possible there, a liquid vapor type behavior.
So this is 1D. In 1D, I'm not sure.
Okay, thank you.
Yeah. But there can be interesting feature of droplet formations in 1D that we plan to address. Yeah.
Thank you very much. Lovely talk.
Okay, I think everyone's ready for lunch. So let's thank